First of all, I would like a very profound thank you to the organizers of the meeting for inviting me and for the wonderful time which we are having here. That's Axel, Juba, I understand, Eric. I was a little bit hesitant choosing the topic on which I was going to talk, because obviously this had to be something related to Ural's scientific activity. Finally, I have found, but you can see traces of my hesitation even in the title of the talk. I was going to speak initially about the two-dimensional early equation. Now it is three-dimensional. But I'm afraid I have to remove my computer because obviously, yes, the projector is also hesitant. Okay, we will do this.
Les ordinateurs. Les cervelles électroniques, comme tous les gens italien. Is this the minute of silence in memory of Karate? Yeah.
Depends on electronic gods.
Ah, the ultimate thing.
So here we are. So my involvement in earlier activity began with a conversation with Ural when we were walking in the olive garden down the observatory, and I was endowed with, I would call in Ural's speak, a sacred crypto knowledge. So, nom de vrai sont un jeu vrai. So you can hear the game of words in this sentence. But yes, using Gebrey nouns was proved really useful in this activity.
That's Pablo is contaminated by this.
Yes, of course, I was also contaminated by Bartos, as you say. But coming to the essence of the topic, I will consider analyticity of solutions of the three-dimensional and two-dimensional Euler equations. And as you can see, Ural's name also appears in this activity quite prominently. So what is known about the solutions to the three-dimensional Euler equation? First, if solutions are initially smooth or smooth enough, belong to this Hilbert class, so essentially have the first derivative, which is Hilderian, then the solution stays in this class at least for a finite time. If the initial condition Vn is analytic in space, then it remains analytic in space, and in fact in a spatio-temporal, in some spatio-temporal region, also at least for some finite time. And so these results are due to Bartos and his Podvedi student Benashuk. In fact, I'm going to repeat this result. They have obtained this result in using quite a subtle technique. They were constructing bounds of approximations of vorticity along characteristics of the Euler equation. They relied on the knowledge of the green function, which is used to invert vorticity to obtain the velocity in space. Yes, of course. And they were heavily relying on the theory of functions of complex variables. As you will see, it can be done in a much, much simpler way. Now, of course, a prominent question in this field is whether a singularity indeed emerges after some finite time evolution of the solution. Some computations suggest that indeed this can happen, and again, there is Birol's contribution to this topic. But basically, all computations have finite precision, even if you produce arbitrarily high precision computations with some sophisticated C++ packages. So no numerical result here can be considered perfect. In fact, there are theoretical results which suggest that the blow-up, not suggest, but which say that the blow-up indeed is possible either if an integral of this form blows up, or
what is the quantity?
Omega,
Ah,
the vorticity.
Omega. Yeah.
Yes. Or if, in fact, it suffices that the direction of vorticity at some point would become singular, so it would not have some constant limit when you approach this point. Also, this problem can be approached from another direction, from generalized equations, and then you can say that if solutions to characterized equations have certain properties, that it's guaranteed that the limit solution will blow up. Now, there is a paper by Forrest-Tamam where certain technique is applied to the Navier-Stokes equation, and this is quite resembling, well, it was an inspiration to me to develop what I'm going to tell you about now, but their method relies on the presence of viscosity, so immediately it cannot be applied to the other equation, it has to be somehow generalized. So, the functional analysis machinery which I am using in this work is, I would guess, basically familiar to all of you. So I am considering space-periodic zero-mean fields, either three-dimensional or scalar fields. I'm considering their Fourier transform. Then, in terms of the coefficients of the Fourier transform, we can define for any arbitrary Q, real Q, of course, a norm which is the norm in the Sobolev space HQ. Generalizing that, we define what is called the Gerbet-Sobolev norm. So here the new exponent emerges. In fact, Gebret's name is mostly associated with Gebret's classes, and in the Gebret's classes, the norm would have another exponent alpha for modulus n, and the classes are defined for this alpha from the interval from 0 to 1.
It's a question of weights, what kind of weights one could.
Yes, of course.
They're exponential, they can be modified.
Yes, of course. But when one starts considering analyticity, it is precisely this case, this norm, when alpha equals to 1, is of interest. Why? Because we complexify our space. So adding 3 more imaginary x's. So we have such a series. We'll consider it now as a function of a complex variable. And then we're interested in the question when this is an analytic function. Of course, each exponent is an analytical function. So we consider a cylinder about the real axis, say, of radius A. Then a very simple computation says that we have a new weight appearing in this formula, namely this one. The complex exponent of a real number doesn't change things profoundly, but this thing, when y is negative, here, can grow. And it is easily seen that if y is less than sigma, which we have here, then this series converges absolutely. And therefore, in the cylinder of radius sigma, our function is analytical. So that's the relation between analyticity and Gevrey-Sobolev norms. Well, and of course there are norms in the back space, also quite standard. There is the Sobolev embedding theorem saying that if we have q derivatives, then the function is in the bag space of that index. For q less than 3/2, if q is equal to 3/2, then that's a boundary case. In fact, if q is slightly larger than 3/2, by whichever amount s, we can prove that the function belonging to HQ is bounded, and the bound can be written down in terms of the norm in this Sobolev class with index 3/2 plus ace. So I'm after finite time bounds for Gevrey-Sobolev norms of the Euler equation. I'm absolutely sure that all of you saw this equation at least one, except for you, of course. But this is the Euler equation. I will, as usually in this game, consider the illustrative case where there is no forcing. So this is just a free evolution of unforced fluid. The fluid is incompressible. The flow, for simplicity, is periodic. And I do not invent new things here. I'm in a cube of size 2 pi. And the flow is zero mean. Again, this is not a constraint because of Galilean invariance of the equation. I can consider the equation in the frame co-moving with the mean velocity. Then I will immediately gain this condition. So I'm decomposing the flow in the Fourier series. The flow is real, therefore these constraints have to be satisfied, and the flow is incompressible, therefore this condition. I introduce a projector onto the plane normal to a vector m, and in terms of this function, in the Fourier space, the Euler equation can be represented in such a form. Ural apparently suspects there is some problem here.
I'm extrapolating.
All right. So I'm assuming that the initial condition belongs to Gevrey class with such indices, and it has the finite Gevrey-Sobolev norm with such indices. And here's the trick which I'm proposing to deal with this equation. I'm suggesting this transformation of Fourier components of the solution. And the function which I'm reconstructing from the new variables w and hat contracted back will give me another function w, in terms of which I will be working. It turns out that this is not an entirely new trick, because apparently something similar was used in a paper by Livermore and Oliver, but well, in my case I am specifying sigma, and this allows me to immediately obtain, to get the term where I will have a derivative of sigma more involved in construction of bounds, and I will get better estimates for higher order index subgroup norms. So for some beta which satisfies this condition, I can make sure that the function w constructed this way has a finite subgroup norm of index 2 plus s. And basically what I would like to show is that this inequality also holds for some finite time.
Without having to write fluid particles.
Without? Sorry?
Having to write complex fluid particles.
No. But I will do something similar in the two-dimensional cases, you will see. Although not complex, they will still be real. So sorry, I'm doing trivial things. I'm not considering anything too difficult. So after this transformation has been applied, in the terms of new variables, the Fourier mode equation takes this form. And if I multiply this equation by such coefficients, I will obtain something like a condition for entropy balance, or some generalized energy balance, whichever, because here the index s plus 1 can be whichever depending on the value of s. And now why
Remind me that w is basically the velocity, but with
yes.
a weight.
Yes, yes. Which also depends on w.
Sure.
That's the idea of this trick. So, and now you see why my substitution is better than the one in Livermore, Oliver. Because here, out of this new term, I'm obtaining immediately a positively defined thing, and moreover, here the index of the subgroup space is by 1 larger than the one which I'm having here. Not by 1 2, but by 1 half. By 1 half. Yes. Anyhow, of course, now I will consider the energy inequality which emerges from this identity. So I will have to consider the absolute value of the right-hand side. This exponent does not spoil my life by the triangle inequality, because this thing is positive, and by triangle inequality, this bracket is always negative. So I just have to find an estimate for the nonlinearity. This is more or less a standard procedure. I represent it basically in terms of functions constructed of absolute values of Fourier coefficients as such an integral, and I use the embedding theorems to obtain such a bound for the right-hand side. And basically we're already done. We have shown that for such a function, the following inequality holds, so what's left is just to solve it. Unfortunately, here the power is larger than 1, so the solution will be finite.
So you're not getting $1 million.
I wasn't asking you $1 million. No. But nevertheless, this quantitic side stands finite on such a, is guaranteed to be finite on such interval. And then, coming back, looking at the substitution which I made and multiplying everything by this exponent, I can relate the norm of the ordinary Sobolev norm of W with the Gervais-Sobolev norm of the velocity. So, I therefore obtain this identity, and because of this bound, on the one hand, I have the first inequality here, and just rewriting what I have above, I obtain the rightmost inequality. Therefore, I have shown that the velocity is analytical in the cylinder of radius which is given by that quantity. This index in the analyticity game is an irrelevant. I thought all of you saw earlier equation, but it turns out you didn't see it. Did you see Berger's equation? No. Sorry. So, well, for your information, it looks like that. And it is the same as Euler's equation, except for we have no the gradient of pressure here, and we do not have Selenium-David constraint for the velocity.
Are you assuming potentiality for the velocity? Or
No, no, no,
Ah.
no.
Because if you're not assuming potentiality, then it's not too much known about it.
But it turns out that for the Fourier harmonics of this equation, I have this system of equations, and I can apply precisely the same trick. So after applying this transformation, I'm getting precisely the same equation now, because I have multiplied it by Wn, and therefore the projection which I used to have in the equation is killed. So this identity is already absolutely the same. It's identical to the one which I obtained for the equation. Therefore, I am obtaining the same energy balance bound, the same energy bound for Berger's equation. Therefore, automatically the same result. If initially the initial condition for the Berger's equation is analytical, then I can prescribe a time interval when it stands analytical. Which means that perhaps all my bounds are too coarse, because the Berger's equation is known to be much worse than the Euler's equation. Worse in the sense of developing shocks, and etc., etc.
Yeah, right.
So it's worse in terms of preserving smoothness. Now, the same trick can be played when I'm considering regularized equations. One of possibilities is regularization by this term, which can be regarded as solid viscosity, dynamic viscosity. It was proposed originally by Ladizhinsky in 1966. It was considered by Ladizhinsky and Askov in a series of papers. Nevertheless, it has emerged about 5 to 10 years ago as under the name of Voigt regularization, because Voigt has suggested some kind of physical interpretation of this term. In fact, it was considered in several papers, but one of the most interesting is due to TT and co-authors. In fact, interestingly, of course, we are relying on the fact in the regularization game. We are relying on the fact that this coefficient is positive. But in fact, such equation can be attributed to evolution of some polymers, so some solutions of polymers, and there you may well have this coefficient to be negative. And again, this was already known to Laskov before 80s, so I'm not sure about how well Voigt's name is attributed here. And of course, this is the regularized equation, and of course it is interesting to see what happens when alpha tends to 0. It can be shown that if alpha squared is positive, then everything is perfect. You can show that when alpha tends to 0, there exist some sequences of alphas when the solutions to the generalized equation converge in some weak sense to weak solutions of the original earlier equation. Then you ask yourself, is the limit unique? And the answer is nothing is known about that, except for when I was doing my diploma paper, I noticed that either this limit is unique or there exists a whole continuum of limit with solutions. I never saw this published and I never published this myself, but I think that's worth mentioning. So again, you can do all these tricks. And this is the final result which you obtain. Again, a similar bound which says that well, except in fact you can write this in terms of function phi, which is given by these identities, and then in terms of phi you find a bound for the radius of analyticity of this solution. Now, the two-dimensional case. Juba tells me that I don't have time to speak about it. In a sense, this is good.
You obtain for all time?
This solution, yes, the solution in the generalized, for the regularized equation, yes, of course, the solution exists, the bound exists for all times. In the two-dimensional case, let me only say the following. There exists a bound due to Bardos, again, back in the 70s, I think Bardos and Benashur, which says that the radius of analyticity is decaying not worse than such a quantity. So this is due to Bardos with covariance. So with my technique, I can only show that in the, so this is the two-dimensional case. The same thing happens, the same thing works, but I have, yes, yes, that's true.
We want better. In numerical evidence, it is a single exponential.
Yes, precisely. That's what you have told me. So the goal might be to obtain that. And it seems that this is possible, but one is not supposed to, one should not consider the Euler equation itself, but one should consider it in Lagrangian coordinates. Then, in fact,
still the Euler equation.
Well, it reduces just to the extent to the equation. Like this, where V is expressed in terms of vorticity very easily, and vorticity stays constant on characteristics. So, well, let me finish.
Is it
this.
that you hope to show that the Lagrangian analyticity strict width is exponential in time, or that the Illyrian one?
First, I'm trying to obtain a bound similar to that for the Lagrangian analyticity. Yes, but then it's a straightforward technique to work out what you get for Illyrian analyticity. So now to the...
I mean, if you take, for example, the one-dimensional Berger's equation with no viscosity, you get a singularity after a finite time in Illyrian coordinates. But things are never go singular in Lagrangian coordinates, because solution is just x is equal to a plus t u0 of a. It never goes singular.
well, that's right, but nevertheless, analyticity in Eulerian coordinates is controlled by how Lagrangian trajectories are approaching each other. So if you have a bound on that, you can produce a bound for analyticity. So now to the final topic of this conference. Well, it is of course this physical phenomenon. Many participants have already voiced their opinions on what's happening there, so let me also give some comments. So first, some observational results. Well, I met Ural in 1990. It was an extremely short encounter with Pan in Moscow, and then I came, it was a very rare occasion that I came, that I was traveling without Olga, to France to participate in Schneeberger seminar. I was met by Ural at the airport. Well, I was a little bit dizzy after the flight, I was shocked by the sun, etc., etc. And this gentleman, rare head at that time, asked me the very first question. So what's new? I thought that to ask such a question, one must have some established background compared relative to which one can speak about something new or not new. And now,
maybe it was a political question.
No. It was a real question, and I remember this vividly as though this was yesterday or several days ago. The thing is, my point is that Ural is precisely about that. He's constantly looking for new fascinating topics, new interesting problems. He gets new interesting results, and then abandons the area altogether because it's not any more interesting to him. And this carries on and carries on. Some, I think, 3 years ago, Ural, with absolutely uncanny expression on his face, asks me, "What, by chance, do you know what is a Hessian?" And with such an uncanny expression, I was absolutely sure that there's some intrigue behind, and indeed it was. So I was asked to solve numerically the number equation. We did that, we wrote a paper, and now still the Hessians are with us. We are doing omnipotential flows, where Hessians are all everywhere throughout the paper. So, I think you are a very singular example of yourself, a very unique one, and indeed a very pedagogical one, because one indeed learns from you this attitude, and we're happy to work with you, we're happy to learn with you, we remain grateful when you give us help demonstrating that we can't write scientific texts, can't give presentations, etc., etc. Many happy returns of this day to you and to your colleagues. Thank you.
So Vlad actually actually went a few minutes beyond this time, but those
Sorry.
few minutes are probably where people were most aptly listening to him.
So I'm surprised there are still so many people around. It was a great pleasure being with all my friends and some new ones even. It's always a pleasure to get acquainted with new people. It was not a bad week. I mean, I am tired now, but usually my expectations are rather low. This has vastly exceeded them.
Thank you.
Thank you very, very much to the organizer. I know that it wasn't a piece of cake, particularly because of funding chaos and so on. You had to carry all this. Luba, Axel, Eric, and I suppose also quite a few people who are sitting in rooms over there. Yeah. And thank you to all of you for having made this enjoyable.
Thank you.
Thank you.
Thank you.